Okay, we're back, and today, with this lesson, we're going to do some calculus. So for many of you, most of you, this will be the first time that you really dive into something that sounds really hard, and it has the reputation of being a really hard class, okay, calculus. You hear that word, and a lot of people kind of panic, thinking that you'll never be able to understand it. As it shows up here, hogwash to that. You've been making graphs for a long time. You've been finding slopes of lines for a long time. If all of that makes sense to you, then you can do calculus, it turns out. One thing that we're good at in math and science and many other fields is we give fancy names to things to sound smart. So for example, today, the main thing that we're going to focus on is something called the derivative. This is a fancy word meaning slope. Okay? Slope of a special type of line, but it's still just slope. And that's what we're going to really dive into. So in calculus, what's cool about it is it allows you to find instantaneous values. So when things are changing, okay, if you're accelerating, if your velocity is changing over time, that might happen at a constant rate, it might happen at a non-constant rate, and that's usually the case in real life. How do you deal with things that are changing? That's what calculus is. It's the mathematics of change. That's how I like to think about it. So just think of what you've done for many years now, straight lines. Okay? How do you find the slopes of things? We know that if you have a flat line, okay, like over here, that means zero slope. If you have a vertical line, that's an infinite slope. Kind of weird. But for anything in between, you can have positive and negative slopes. Uphill is a positive, downhill is a negative. Think about your definition of slope over the years. I still remember it from many, many years ago, rise over run. Okay, or delta y over delta x. Okay, the delta is a change in something. How do you find the change? Well, you have to subtract two values. Okay, so this is why you need 2 points on a line to figure out the slope. So we can plug it in here and find that rise and find that run. Okay. So slopes, it turns out, can have physical meaning depending what you're plotting on your graph. Now that'll come in the future. We're just going to want to get to the basics today and keep it general. So what people like Newton were starting to think about many years ago, 350 plus years ago, is what if your graph's a curve? Okay, does slope have a meaning if something has a curve? And it turns out that, well, we can kind of reason it, I suppose. And we still need 2 points. Okay, we're just going to use our definition for slope, okay, the usual definition. But you need 2 points. And so if you wanted to find the slope of a curve, where's the other point? Where's the second point? Let's say that this red dot here is where we're trying to find the slope. Well, let me choose just kind of arbitrarily a second point up there. That'll be my x2, and it'll have a y value, y2. Now we're looking at the function specifically. Let's keep it the simplest curve. Okay, the most basic parabola, y equals x squared. Okay, that's the equation that gives us, this kind of graph. Well, let me play just a short little video here. If we think of the line between these 2 points, okay, something like that, that's called a chord. And yeah, should we call that the slope of the curve at that particular point? Or is there a better way of doing it? Okay, so here, let me just go and switch to a video that'll just have a little picture in your head of what we're about to do.
To determine the slope at a particular point, here for example, simply take another point on the hill. It doesn't matter where. Now connect the 2 points with a straight line. That line is called a chord, and its slope depends on the location of the second point. If the first and second points are reasonably close, the chord is a reasonably good approximation of the bike's path. Now, move the second point closer to the first. Move it even closer. The slope is a number, and as the points get closer together, the number gets closer to a certain value. It's reasonable to call that number the slope of the hill at that point. The line with that slope through the point is called the tangent line. And the tangent line is just what the chord turns into as the points get closer together. And the slope.
Okay, so that's the gist of it. Now let's play with the math. Let's play with our slope equation for this. Because after all, we want to try to figure out what the actual number is for the slope. What's the actual value of the slope? So the difference between those two x values, okay, that little gap that's right there, we use the symbol h. That's just, you know, whatever the difference is between the two. So I'm going to say that x2, that x, it's value of that second point that we chose to make our chord. We're just going to add x1 plus h together. H, this I believe is the symbol they tend to use in most of the school's calculus classes. We'll try to keep the notation similar. Let's make some substitutions into our slope equation based on this graph, based on our picture. Okay. So the y values for any x value are given by the function. Okay, so what that means is the y value of the second point, y2, is x2 squared. The y1 value for the point that we're after would be x1 squared. Okay. And now x2, I'm going to substitute in x1 plus h, and we have to square that, minus x1 squared. And in our denominator, x2, I'm going to substitute in x1 plus h, and we have minus x1. Okay, I'm just substituting using our function. Okay, now let's just do algebra. Let's simplify our numerator and denominator. So on top, we have to expand that. We have to square that quantity. x1 squared, 2x1h, have an h squared. Okay, that's the quantity squared. Then we have an x1 squared that we have to subtract. And our denominator, the x1's just cancel out, and so we just have h in our denominator. That'll be the case every single time we do this for different kinds of functions. Keep simplifying. The x1 squares cancel out. And now the two remaining terms on top there, there's a common factor of h that we can divide out. So what we have left after our substitutions and simplifying is an equation for the slope of our chord. That first term will just be 2x1, and then we have a plus h. Okay. Now, from what the video said, what we're after isn't that particular line. Okay, the chord, the slope of the chord is just an approximation of the slope at that red point that we're after. What we'd really like to do is to get what we call the tangent line, the slope of a tangent line. Tangent lines are lines that touch a curve just at that point that we're looking at. And that's what we can say, that's reasonable to call that the slope of the point. Now keep in mind, if we wanted the slope at the second point, okay, if the tangent line there, check it out, it would be quite a bit steeper if we drew that tangent line in. So that it kind of shows how, as you go up the curve, the tangent line is getting steeper and steeper. It's the tangent line, or what we call the instantaneous slope. That's what's changing as you go. How do you get it? Well, to get the chord closer to the tangent line, like they showed in the video, you have to take that second point and slide it down the curve, and that'll bring that chord slope closer and closer, a better and better approximation to the tangent line. How do you do that? What's changing if you want to make that second point get closer to the first? Well, we have to take that x2 value and kind of slide it down the x-axis closer to x1. It's the h value that we're changing. Okay, that difference between the 2 points. So if we can make that h really, really small, that second point gets closer and closer to the first, and we get a better and better approximation. Okay, so this equation here, just from the normal slope equation, is really just an approximation of the tangent line slope. You want to make it exact, though. So here's the trick. This is what makes calculus. Calculus gives us exact slopes. What we're going to do is, in math, what's called a limit. We're going to take the limit as h approaches 0. Okay? As we bring that second point closer and closer to the first, in your head just gets unimaginably close. Okay? Or a term you hear in calculus, infinitesimally close to that first point. Where that h value gets so small, effectively it doesn't really matter anymore. And whatever h is left in your slope equation, it becomes 0 for all practical purposes. And whatever's left over, in this case, 2x1, that's the exact slope at that point. Okay, so if you were to map it out on a piece of graph paper, okay, and you did it to scale, you drew this parabola perfectly, choose any x value that you want, x equals 2. Draw the tangent line on your graph and measure, like physically measure the slope. Well, if your x value is 2, this is saying that the slope at that point is 2 times 2, which would give you 4. The slope at x equals 10 would be 20. At x equals 100, you'd have a slope of 200. This would be exact. Okay? And it's this process that we can use to calculate for any function. Okay? Keep in mind, as soon as we change the function, as soon as we have something other than y equals x squared, we have to do this algebra with the slope equation and find out what's left over when we do this limit. It's this limit right here that's kind of the magical part that gives you the exact answer. The only other thing I'm going to do here is think about, notation. Notation, trust me, is half the battle to understand calculus. It's going to look new to you. You have to get used to it. What we're doing here is we're doing the limit as that gap between your 2 points approaches 0 on the normal slope equation, which we usually write as delta y over delta x. Rise over run. Well, that's a lot to write, and I'm just as lazy as anybody. I don't want to keep writing that limit every time we do this. Let's change the symbols. Let's keep it looking like slope, but all I'm going to change are the deltas. I'm going to change the deltas into d's. dy over dx instead of delta y over delta x. So it's still slope. It's still rise over run. It's just that the points that we're looking at, the difference between the y1 and y2 and the x1 and x2 are incredibly close together. They're really small. That h is around 0. This is the notation of what we call the derivative. And the derivative is just a fancy word meaning slope, not just any old slope, but the slope of a tangent line to a curve. And this is calculus. Okay. So I hope this example makes some sense, just to introduce the notion of a derivative and how we can find one for the simplest curve. We're going to get some practice in class doing this algebra for some other different functions, similar to this, but a little bit different, and seeing what we get for that final answer of the slope of the tangent line. We're going to find derivatives. Okay, so I hope this helps a little bit, and we'll have a lot more practice with this. But until next time, we'll see you later.